Hello, this is Dr. Liu, and in this video we have a second example of free fall. We have the formulas already here that I wrote in the previous video, and this question is again from University Physics, published by OpenStax, Chapter 3, question number 71. A diver bounces straight up from a diving board, avoiding the diving board on the way down, and falls feet first into a pool. She starts with a velocity of 4.00 meters per second, and her takeoff point is 1.80 meters above the pool. We have three questions. A. What is her highest point above the board? Let's just assume that's her feet, because we don't really know how tall she is. B. How long a time after her feet in air? So basically, how long in terms of time between jumping off the diving board and her feet hitting the water? And C, what is her velocity when her feet hit the water? So how fast, right? So if we take a look at these questions, these two questions are related. How long are her feet in the air? So okay, her feet in the air, that is between jumping off the diving board and hitting the water surface. Velocity of her feet hit the surface, hit the water. So that is also that same final condition, hitting the water. But question A, on the other hand, is asking something completely different. What is her highest point above the board? So highest point above the board. So this part is not where she actually hit the water with her feet, right? So let's draw a diagram to help us understand what's going on here. So here's a diving board, and well, let's draw her tall enough. Trying to jump off, taking a pose. Alright, so what we know about is that the takeoff point right here is 1.8 meters, so 1.8 meters. Let's say here's the water surface. And she jumps up, so let's just draw a trajectory. She jumps up, comes down, feet down first. Well, let's maybe redraw this. I don't think her feet can go up that high. Let's be a little more realistic. So maybe her feet goes up this high and comes down and hits the water. So that's where her feet contact the water. So this is the highest point, right? This is highest point. So I can call this X max. And I can also set up a coordinated system because we know the 1.8 meters, and we don't really care about anything after her feet touch the water. So we can set our origin right at the water surface. So here's a 0. And I shall point the axis upward, just like this. So here's her maximum height of her feet, very bouncy board, right? This is her initial height, her feet, and final at the water level. So we're basically talking about on the way up here to a maximum. Now, not exactly all the way down here where we were asked how long, the time it takes, this whole thing, right? And also how fast her feet hit the water. So it's right here. And we should treat this position as the final. And then later we can solve this other part, treating this as final. So either way, the initial position, it should be 1.8. And the final position here is an X max is an unknown height. And her initial velocity 4.0 must be upward, right? 4.00 meters per second. So her final velocity at the maximum height, well, we weren't given that, but if you think about this a little hard, then you may realize, oh, her final velocity must be 0 because otherwise she would still be going up, and this whatever maximum height is not the maximum at all. But then she will just eventually stop in mid-air, then she will reach the maximum height, right? So time we don't really know. Basically, we know that max height is a hint for final velocity equal to 0. That's right. So that's a hint here. And you could also say start from rest, drop something from rest. That means initial velocity is 0. It's not here, but I just realized that I should mention that. So okay, so this is our list of parameters, and I'll use the equations. So equation 1, this is the maximum height. I can put the max here, but it doesn't really matter, I know. This is 1.8 and 4.00 times time minus, as we said already, 9.8 and half, that's a 4.9. We should get used to this value, and t squared. Okay, so there are two unknowns, the t and the x max, so we can't really solve it. We can leave it here and just move on to equation 2. We probably should have started with equation 2, but that's okay, we can go back to equation 1. So equation 2 has final velocity, which is 0 at maximum height, and initial velocity is 4 minus 9.8 times time. So this should get us the time. So 9.8 time is equal to 4.00. So time is equal to 4 over 9.8. This is close enough to 4 over 10, right? So 4 over 10 is about 0.4. So I bet this is 0.408. So let's check it out. Calculator here. 4.00 divided by 9.8. Is that 0.408? Okay, 0.408. Alright, so 0.408 seconds later, she's at her highest height. Okay, so now we can use this. We can plug this into equation 1, right? So t plug into equation 1, we have x max equal to 1.8 plus 4 times 0.48 minus 4.9 times 0.408 squared. Okay, so 1.8 plus 4 times, this underscore is the answer of the previous step, makes it easier, 4.9 times underscore squared. Okay, so 2.62, because we're carrying, we have 3 sig figs, 2.62. So 2.62 meters. Okay, so the original question was her highest point above the board. So if this is 2.62 and this is 1.80, then this difference, this is that height, right? So the height is 2.62 minus 1.80. So 1826, that's 0.8, and there's also 0.02, 0.82 meters. And sometimes with subtraction, we could lose sig figs. See that we now have 2 sig figs after subtracting 2 very similar numbers, each with 3 sig figs. Okay, so this is how high above the diving board her feet stopped. Okay, so let's move on to the next part where she falls into the water, almost hitting the water. Oops. All right. So okay. One thing to remind you is this whole motion is actually entirely described by these two equations, not just the up part, not just the down part, but the whole part. So if you wish to use this diagonal still as the initial condition, initial height, initial velocity, and use that as a final, new final, you should be just fine. You don't have to start from here as a new initial and then come down here as a new final. That's not necessary. This equation, system equations, can deal with the entire motion while she is under only gravity. So let's give that a try. Okay, so what I want here is to borrow this list. Oops. Alright, so now we have the list. The initial position is still 1.8. And now the final position down to the water level is 0. And initial velocity is still 4.00. Just like it never happened, this part that we solved, it's just part of that motion. We didn't really have to start from here and come down. We just start from here, go all the way up, right? This is a smooth curve. And the final velocity is unknown. And the time of her feet in the air also unknown. So that's fair. We have two unknowns and we have two equations. So let's start with equation 1 again. Zero final velocity position is 1.80 initial plus 4.00 times time minus the half g, right? 4.9 t squared. Okay, so now we are dealing with a quadratic equation, right? This is the a term, b, and that's the c. So we can solve, and let's write this down. Let's write it out. T is equal to 1 over 2a. 2a is doubling that back to negative 9.8. Minus b plus minus b squared minus 4ac. 4a is a negative. Let's keep that count. And okay, here negative is negative, right? Times c, 1.80. Print out my ruler. Okay. So we get t equals, let's get the calculator out. I do remember that I have that quadratic solution, right? This function right here. Okay, so just hit that and we'll just type in ABC. So minus 4.9 is A. Remember, the A is the quadratic factor, and B is 4, and then C is 1.8. So we should get 2 times. Okay, so minus 0.322 if I round to even, right, with 3 digits. 322, 1.14. Okay, so 2 separate times, and we know this has to be the positive time. She has to jump up, and she spent this much time in the air before she her feet hit the water. So it has to happen after she jumped off, not before she jumped off. That would be ridiculous, right? Okay, so let's keep this and we'll toss that. And we can take this answer to our equation 2, where we can get the final velocity. Okay, so 4.00, I think I can just type it up, 4 minus 9.8 times 1.14. So we got a negative velocity, 7.17. It makes sense because she's coming down and getting into the water, right? So minus 7.17. meters per second. Okay, so since it is just 15 minutes, I can talk about this negative solution a little bit. So over here, we still have this diagram. So let me see if I can borrow this diagram here. See how much I can borrow. Alright, I just borrowed the diagram. Okay. Didn't get the water over, but that's fine. I'll just redo the water. I'll move it over here. Okay, that should be good enough. I'll just redo the water surface. And this is her trajectory more or less. So this is time equal to 0 at her feet right here. So this is time equals 0, and that is time equals 1.14 seconds. So where did that 0.322 second come from? Is it just a mathematical artifact? I agree it is kind of an artifact, but it still has some meaning. So let me extend this trajectory here. So assume that there's a Doppler-Ganger of her, and the Doppler-Ganger of her, she was just looking at the water level. She actually somehow jumped up, and that was before this actual her jumped off the diving board. So the Doppler-Ganger started here, jumped at a certain upward velocity, and at time equal to 0 they exactly start at the same point. They both come up and go down. So this is when the Doppler-Ganger actually jumped. This is t equals minus 0.322 seconds. I know that we don't have a Doppler-Ganger here, but this is kind of a mathematical thing that we're actually looking at more or less a trajectory of a projectile, right? Because this is an upside down parabola with a quadratic term. So we're talking about at which time the parabola somehow cuts through the 0 height. An upside down parabola should cut through 0 height in two places, right? So if you have the 0 height and you have this parabola here, and as time progresses, she's not really jumping forward. This is just stretching over time, so we can see that as time starts, she starts from here at the jump, the diving board. She goes up, comes down, right? But a mathematical parabola is a continuous infinite thing, so it's got to be having two separate intersections, which means this is t equals 0. This is t-axis. This is the position x-axis. So she goes up, comes down, and there's this negative time where this curve actually crosses the 0 height, the water surface. But we know she didn't really happen to be here because she started her free fall from here, from up here, right, or here. But it's interesting to see this kind of a Doppler-Ganger effect that mathematics doesn't really know what we're using it for. We know better. We start our projectile from this point. So let's see. This is the actual projectile, right? And it kind of stops here. So it never goes below the water surface because she gets some resistance on the water, right? So this limited version of a projectile or an upside down parabola, this is our free fall region. Outside the region is not free fall. Mathematics just doesn't know it. All right, thank you.